Well, here we are at kinetics. Now, we've already covered the instantaneous rate law. We're going to focus now on the integrated rate law. Quick review, the instantaneous rate law will give you the rate of a reaction if you know its concentration. Here we've got a zeroth order, first and second, which are the exponents here. And if you know the concentration is 1 molar and you know the rate constant, you can find out how quickly that reaction is going. But that's a fleeting answer, because as this reaction occurs, it will be 1 molar only for a fraction of a second as it is used up. And then the rate changes for first and second order reactions. Not so zero order, but zero order is pretty rare. We're going to focus primarily on first orders, though. Now, the integrated rate law is an expansion of this. It allows you to see how the concentration changes over time. Now I can know, hey, I know what the concentration is going to be after so many seconds, or after so many seconds, what will the concentration be? So this gives you specific concentrations over time. This is a very useful series of laws, and it's different for the zero, first, and second order, because these are the integrations of the change in rate over time, and that's how we derive these equations. Thank you, calculus. Let's go right now and focus on the first order reactions. Here's our problem. Complete this table for a first order reaction based on its concentration versus time data. And we're given this very nice graph that shows us what happens to the concentration. Here we've got our 4/10 molar that we start with. And as the reaction occurs, we run down to these various concentrations because A is being used up in this reaction. How are we going to fill out that table? Well, here's a series of steps that you can follow whenever you've got a first order reaction problem. If you have a concentration versus time graph, good, or a natural log of A versus time graph, you can solve very often by finding the slope of the natural log of A versus time. This is where we can find this valuable K, which is useful both in the instantaneous and the integrated rate law. So let's go back to our problem, because that was the first thing we needed to solve, is to find this important K. Now, we're not given the natural log plot for this reaction. If we had, we could have used it. I'm going to bring that up right now because this is one of the methods in which you can find K. Here's this same graph, but instead of having concentrations of A, I've got the negative log of the concentrations. Instead of having molar, we've got a log number. Notice that we have negative values, which is true for any logarithmic value between 1 and 0. We've got 0.4 down to looks like about 0.6, 0.7. And that produces a negative exponent. If you take E, the 2.71848, and raise it to the negative, it looks like a 0.9 value, you'll get 0.4. The natural log of 0.4 is this negative 0.9. Just means that's between 1 and 0. So you're going to see negative values a lot when you do these logs. That's not because the concentration is negative. It's because we're dealing with logs. Now, if we had this graph, we could find the K value from its slope, but this is a tough one to figure out because we don't have the in-between lines here. We're going to have to do some estimating, and if I had to do the slope for this to find K, I would have to figure out the drop first. Again, our drop over how far it goes, and here at the end of our graph, looks like we're at about negative 2.6. I'll put that down, negative 2.6, and that's an estimate. You know, that last value is not going to be good. And of course, if you're doing a slope, we have to find out the difference. How far did it drop? And as I said before, this looks like about a negative 0.9. And here we'll see that's a drop of 1.7. We're going to go across. It takes 250 seconds. That our x change is going to be 250. So I'll take that drop and divide it by the 250 and see what we get to estimate the K. Here we go. Oh, looks like it's about negative 0.0068 is the slope. In the case of finding the K for a first order reaction, the negative of the slope. So our K is going to be, according to this estimate, 0.0068. But there's a better way of doing this, and that's what I'm going to focus on right now. I'm going to go back up to here without the log table, and I'm going to go to method number 2. Most first order reaction rate problems, and when I say most, I'm saying 9 out of 10. Really, most first order reaction problems can be solved using half-lives. And remember our half-life equation here. Let me get to it again. I'll get to our graph here for kinetics. Here's our AP chemistry equation constants. This is on page 1, and here on kinetics, they give you 3 integrated rate laws: zero, first, second order. They don't label them. You're supposed to know that. But here's a real key equation. It's beautiful. The half-life is equal to 0.693, the natural log of 2 divided by k. And of course, we can switch this around. K is going to be equal to 0.693 divided by the half-life. And you should memorize that 0.693. It's an easy number. 6, 3, and 9, 693. Let's go to our problem again. Examine the data to find a half-life. Now, first order reactions have constant half-life. So if you find a half-life anywhere in that graph, it's going to be valid. Once you know the half-life, you can divide it into 0.693 and they'll give you the K. Or if you know the K, you can divide that into 0.693 to get the half-life. But we've got our graph. Let's go back to the graph. Here it is. Here's our graph. And see if we can find a half-life. Like 90% of the time, you're going to see a beautiful half-life in the problem. They set these things up. Here, let's see, we have a 4/10. Half-life would be half as much, 2/10. Oh, right there. Took 100 seconds. We know the half-life is 100 seconds. Let's say you didn't go from 4/10. Let's say you went, here's another nice point, an intersection, 2/10. Here's 2/10. Well, what's half of 2/10? 1/10. And again, let's see the time span. At 100 to 200, it's still 100 seconds. That's the key. That's the proof of a first order reaction. Then we can figure out the half-life. You probably won't need a calculator for that. I hope you don't need a calculator. But it would be our natural log of 2. I'll put that down right now. Natural log of 2, just so you can see that it's 0.693 divided by the time, which is 100 seconds. Oh yeah, I need to do that on a calculator? No. There it is. 0.00693. I wasn't too far off when I estimated using that natural log curve, but this is a much more accurate, and it's also, I think, a faster method. Easier, certainly. Once you find a half-life, divide it into 0.693, and you've got this all-important K. Let me put that down. 0.00693. In fact, let me make that a nice red to show that we calculated that. Notice our unit is per second, because when we multiply K times the concentration, we get the rate, which is in molar per second. For every first order reaction, the K unit is second raised to the -1, or per second. In fact, if you just wrote down 0.0693 for an answer for K, even though you did this calculation, it'd be marked wrong if you didn't include the unit per second. Now be careful. Sometimes on exams, they'll have minutes or hours. So focus, okay, this is per second. If the question is per year, then you do it per year. Don't lose this calculation because you presumed it's always per second. Okay, we've got the first part taken care of. So that's very, very good. Now let's go on to the other questions. Okay, our next question that we have on this is finding the concentration, the molarity, at 300 seconds. We could go to our graph here and look at 300 seconds and we might be able to estimate it. You figure, okay, this graph's going to be going around here, and somewhere around here is where our answer is going to be. Now, going back to our instructions, here on 2, it says most first order reactions can be solved using half-lives. Remember I said 9 out of 10 questions are going to be solved using a half-life, and you keep looking for them. So always think half-lives on these rate law problems for first order reaction. This doesn't apply to zeroth order, which you almost never find. There's never been a zeroth order question yet. It won't apply to second order, which sometimes shows up on exams. So let's go back to our problem and think half-lives. Half-lives. Okay, we know the half-life is 100 seconds. We found that out earlier. And if we had been given a K, we would have divided into 0.693 and found the half-life if we couldn't find it on the graph. But almost always you'll be able to spot it quickly and easily. We start at 0 seconds, and now we're going to 300 seconds. We know the half-life is 100 seconds. After 100 seconds, we went from 0.4 to 0.2. After another 100 seconds, 2 half-lives. We're now down to 0.1. 300 is another half-life, which is half of what we started here, 0.1, we're going to be at 0.05. That's what the answer is going to be. The concentration is 0.05. I would say that to 3 significant digits because we've got our K to 3 significant digits and our half-life to 3 significant digits. 5/100ths molar, 50 micromolar. Easy, fast, no need for fancy math. It's just an extra half-life after our second half-life here. From 100 to 200, from 200 seconds to 300 seconds, we would end up having another half-life right here, right on here. That's where we'd have this next dot. So that's beautiful. We've gone back and said, okay, examine the data and find the half-life data. It's going to help you. Perfect. Now for our next problem, if we start off at 4/10, we find that our concentration has dropped down to 0.0667 molar, 66.7 micromolar. How long would it take? How long do we have to wait to go from 4/10 molar down to this really, really low concentration? If we follow this down, we realize that this graph ended at 250 seconds, where we had a concentration that'd be sort of something that we'd have to estimate. And, it looks like it's close to that value, but I don't know. Now, I said, remember, that, look for half-lives. 9 out of 10 cases, it is half-lives. But here, there's no halving. I mean, we've started at 0.4, half of that is 0.2, half of that is 0.1, half of that is 0.05. This is in between there. So our half-lives aren't going to help us here. This is the 1 out of 10 chance where we've got to go to the equation sheets and actually use this equation for the first order reaction. That's where we'll go next. Here's our next. We know we're going to try and find the concentration at 0.0667. It's going to be between 250 and 300. Let's use that equation to solve. That equation has us take the natural log of where we're going to end up with, which is 0.0667 molar, somewhere around here, minus what we started with, 0.0, a natural log of 0.4 molar, is going to be equal to, again, don't forget this negative sign, 0.00693 per second times time. So that's going to be the equation. It sounds nasty, but really it's not too tough to solve if you end up using your calculator. In fact, let me pull my calculator up right now. Here we go. I'll take that natural log of 0.0667, and from that, I'll subtract the natural log of 0.4. That'll also be a negative number because it's less than 1. So our difference in our logs is going to be negative 1.67, and we just have to divide that by our little 0.00693, and I'll include that negative sign so we don't get that negative time, which doesn't happen too often. I'll have a demonstration later on where we'll do negative time, but that's in another video. 0.693. Okay, we're set. We should see what our answer is going to be. There we go, 258 seconds, which, let me see. Yep, that's going to be somewhere around here. I thought maybe a little bit further, but we've got our calculation right there. Let me just pull the rest of this down and show how we've done that calculation. And also, we could have done it another way. If you're clever with logs, you could have just done the natural log of 0.0667 divided by 0.4 divided by this. Saved you the entry of a log, but let's put that 258 seconds in our answer, and we're on our way to completing that table. 258, and the seconds unit is there. Be careful. Sometimes they'll have minutes, sometimes hours, days, or even years. So make sure that you're following whatever the question gives you. In our case, it's seconds. Now for this last one. This one's the trickiest of them all. That's why I saved it. What's the concentration at 350 seconds? Well, 350 seconds, half-lives, we can get 300 or 400 seconds. But in between, it's not going to be halfway in between because this thing gradually changes. So don't try and figure out what the difference between these two is and try and go halfway there. Now, we're going to have to use our equation again. Let's go there next and use that 1 out of 10 times equation for the first order reaction. We've got our setup, we've got our equation, we've got our known values. We're ready to solve. But before we do that, just to take a quick look to sort of estimate what the answer is going to be, we're looking for a concentration at 350 seconds. Well, we know at 300 seconds is going to be 0.05, and at 400 seconds, which is another half-life, it's going to be down here at 0.025. So our answer is going to be between 0.025 and 0.05. Let's see if it turns out to be that way. Substitute our values, and there would be the way we'd solve it. We would end up taking our KT, negative KT, and add the natural log of 0.04 to it. Calculator time. I'm going to clear my previous answer. Work on this one. I'm going to move this out so I can see all the values as I'm doing it. It's going to be the negative 0.00693 times our 350 seconds. That's how long we're going to be running this. And then we just have to end up adding, because here we have our negative ln, be careful with the signs, adding to that the natural log of 0.4. We've got ourselves a negative 3.44, and this is where you'd say, okay, we've calculated our 3.344, we've calculated our negative log of the AT, and this is where you've got to be good at your logarithms. You're going to have to take an anti-log. That's our next step. We're going to get the anti-log of this, which is what we'll get our calculator for. I'm going to reverse my log. Instead of taking ln, I'm going to go second function anti-natural log and put in my last answer. I could type it in again, but really it's good practice if you've got a little memory where you can put that answer in to use it. This way you won't mistype it, and see if we get that concentration we expected. And here we are, 0.0534. We had, let's make sure that that's what our answer is going to be, and that's what I've got in my calculator. We anticipated between 0.25 and 0.05, and indeed our answer 0.0354 is that, and we can put that into our last box on the table. Here's our table. And I'll get my calculator up to make sure I get the right value, 0.0354 molar. And we'd expect it to be right about there. Yep, that's going to look real good on the graph. It makes sense. This is an answer that makes sense. It's probably the most difficult type of calculation you would have on the first order rate law problems. Well, we've been focusing on just the first order reactions. Let's compare the first order with the zeroth order and second order reaction. I've got a new experiment set up where we've got our zeroth order and first order and second order beakers filled with a blue dye that's going to be bleached out. If this is a zeroth order, our constant for this we've set up as 1/10 molar per second. The constant for the first order is exactly the same, except its unit will have to be per second, and the second order will have to be per molar second for the rate to work out. So we're going to get this started, and we're going to see how the concentrations of this blue solution run through with the same rate constant, but using a different mechanism. A zeroth order where you'd only have either a enzyme catalyst or a surface catalyst. Our first order where just the concentration of A raised to the first power, and then of course the second order where A has to collide with itself so that it's going to be A squared. So let's get this reaction going. Well, here we are at the end of the experiment. After 50 seconds, we can see what happened to all of these orders. Our zeroth order just crashed almost immediately. Every second, we lost 1/10 molar, till after 10 seconds, there wasn't anything left, and we had a perfectly clear solution. Again, very unlikely reaction. Now, our first order, you can see changed quite a bit. There's just a faint little blue left in there. It started off very, very nicely, almost as well for the first second as the zeroth order, but then as the concentration of A decreased more and more, the reaction rate slowed down and slowed down. So you can see here at 20 seconds, we're at 0.15 molar, while at 20 seconds, the zeroth order is finished. Our second order will slow down even more. We're decreasing these concentrations and the effect is by the square. So you're going to have to be a very, very patient person to watch this reaction to go to completion. It's going to be a long time before this solution becomes clear and we've lost all of our blue. But let's look at this more closely in terms of rates of reaction. I've examined here the rates of the reaction, the speed at a specific instant using our instantaneous rate law for 0.5 molar. We've got each one of these reactions and we're going to calculate the rate at 0.5 molar. The zeroth order had a rate of 0.1 molar per second. Finding that slope is pretty easy. You just take that 0.5 raised to the 0 power, making it 1, and then we get 1/10 molar per second. Finding the slope of the first order is a bit more difficult in terms of drawing that line, but you can calculate it very easily because we just have to take 5/10 times our rate constant, 0.1. And here you can see we've got a rate of 0.05 molar per second, half that. At this instant, our 10-second instant where we've got 0.5 molar, we've got a rate that's half of that. And that rate's going to decrease gradually because the concentration of the blue dye is going to decrease also. Finally, with our second order reaction, we take that 0.5 molar and we square it and multiply it times our rate constant, the 0.1, and we get our 0.025 molar per second. As you can see, that slope, the slope of that line, is not nearly as steep. It's half the slope of our others. Well, with this, you can see we've covered the instantaneous rate, we've covered the integrated rate law, we've seen the graphs and how to interpret them. So you're now a specialist on rate laws and rates of reaction.